Cruise ship physics midterm. Work occurs when a force is applied to an object and that object is displaced. This means that that object's energy is changing. In order for work to happen, the force has to move the object that distance. This occurs on the cruise ship when playing ping pong. The player lifts up the ping pong ball a given distance and uses their body as a force to do that distance. The ping pong ball has a change in energy with this. We can use the equation work equals force times distance to solve for the amount of work done. We know that the force is 0.9 newtons and the distance is 0.7 meters. We can multiply it out. We know that the work is 0.54 joules or 0.5 joules with correct significant figures. Gravitational potential energy is energy that an object has because of its vertical position above or below a zero reference level. If the object is above a zero reference level, it has positive gravitational potential energy, which means it already has enough stored energy to come down to the zero reference level by itself. If the object is below the zero reference level, it has negative gravitational potential energy, and that means that it requires more energy to be brought back to the zero reference level. This energy is potential energy because it's not being used, but it has the potential to be used. An example of this is when the rock climber is climbing. They have a height which gives them potential energy. If they were not holding onto the wall, they would fall down to the zero reference level, which is the ground. We can use the equation Ug equals mgh to solve for the amount of gravitational potential energy. We know that the mass of a person is 70 kilograms, and the acceleration due to gravity is 9.8 meters per second squared, and the height is 7.5 meters. So we can multiply them out and we get 5,145 joules or 5,000 joules of energy if we include significant figures. Elastic potential energy is energy stored as a result of deformation of an elastic object, such as the stretching of a spring. The amount of energy stored has to do with the type of the object and the amount the object is displaced. Any object that can be deformed and returns to its natural position afterwards can be used to store elastic potential energy. On the climbing wall, the climbing rope is made of a slightly stretchy material, because when a climber falls, the rope is supposed to catch their fall, but not put all the force in their harness at once, so it stores a little bit of energy in its elasticity. In the diagram, we see that this rope is being stretched. We can use the equation Us equals 1/2 kx squared to solve for the amount of elastic potential energy that is stored in the rope when a climber falls. We know that the spring constant of climbing rope is 450 newtons per meter, and we know that the displacement of climbing rope when a climber is to fall off is 0.2 meters. So when we multiply it out, we get 9 joules or 9.0 joules of elastic potential energy with significant figures. Kinetic energy is energy that an object has because it's in motion. The object is changing its position and changing its location, which means it must have energy because that's the only way that it can move around. An example of this is when the ping pong player is playing ping pong. The player himself is moving around the court in order to get the ping pong ball on various ends of the court. Since the player is moving, the player itself has kinetic energy. The equation for kinetic energy is Ke equals 1/2 mv squared, where m is the mass and v is the velocity. We know that the average mass of a person is 70 kilograms, and from sources online, we know that the average speed of a ping pong player is 6 meters per second when they're playing ping pong. So we can multiply these out, and we get that the kinetic energy is 1,260 joules or 1,000 joules if we include significant figures. The law of conservation of energy states that all energy is constant in the universe, and no energy can be created or destroyed. This means that all the energy before an event is still there after the event, and no new energy was created or no energy was lost either. And this means that the amount of energy doesn't change, but the form of that energy, whether it's potential or kinetic, the energy can change between the forms. An example of this is when playing shuffleboard. The player starts by pushing the disc, and when the disc is in motion, it has kinetic energy. However, eventually, the disc stops at the end of the table. And when the disc stops, it has no potential energy and no kinetic energy. But we know that that energy had to have gone somewhere because no energy can be lost. We can use the equation for conservation of energy, which is the sum of the kinetic, potential, and radiant energy before an event is equal to the sum of the kinetic, potential, and radiant energy after an event. So before the event, we know that there is no potential energy and no radiant energy because the vertical position is not changing and there's no radiant energy either. But after the event, we know that there is no potential energy because the vertical position didn't change, but we know there's also no kinetic energy because the object is not in motion anymore. So we know that all the remaining energy has to be radiant energy. Since the mass of a shuffleboard puck is 0.6 kilograms and the average speed of a shuffleboard puck is 5 meters per second, we can solve for how much energy was lost due to friction, which is a form of radiant energy. And we can get that the amount of energy lost to friction is 7.5 joules, or 8 joules if we include significant figures. Mechanical waves are waves that propagate through a medium at a wave speed that depends on the properties of the medium. There are two basic types of mechanical waves. Longitudinal waves, for which the particles move in the direction of propagation, or transverse waves, for which the particles move in the opposite direction of propagation. And that's the oscillation motion of the particles. So mechanical waves carry energy through particles, and with multiple particles in simple harmonic motion and in sync, that's how you create a mechanical wave. An example of a mechanical wave is the sound the diving board creates when it hits the mechanical stop. After somebody jumps off the diving board hits the mechanical stop and creates a sound. Sound is an example of a mechanical wave because the particles are the air molecules and they oscillate back and forth in the form of a longitudinal wave. We know that the sound that a diving board makes is 75 decibels, and when put into an online converter, we know that 75 decibels is equal to 0.0562 for an amplitude. The energy is proportional to the amplitude squared, so we can use this equation to solve for the amount of energy. If we square the amplitude, we get that the energy is equal to 0.0032 joules. Electromagnetic waves are waves that can carry energy through an empty space. Electromagnetic waves do not require a medium to propagate through, and so the particles that move in an electromagnetic wave are photons, and they carry packets of energy. So unlike mechanical waves, they don't require a medium to pass through. Examples of electromagnetic waves include radio waves, ultraviolet rays, X-rays, and light rays. When closing the lid of a tanning bed, the user accidentally closes it on his hand. His friends think that he could be injured and they take him to the doctor. The doctor performs an X-ray on his hand to make sure that his fingers are okay and none of his bones are broken. This is an example of an electromagnetic wave. Radiant energy is the energy carried in an electromagnetic wave. This form of energy can travel through space. For example, the heat that we receive from the sun does not travel through air, but it travels through space, and this is and it's a vacuum, and this is possible through electromagnetic waves. If we reference the X-ray example, we can calculate the amount of energy in those X-rays. Using the equation E equals hf, where h is Planck's constant, 6.63 times 10 to the negative 34 joules per second, and the frequency, which is 3.0 times 10 to the 16th power hertz, as specified on the X-ray machine, we can multiply it out and we know that the energy is 1.989 times 10 to the negative 17 joules, or 2.0 times 10 to the negative 17 joules if we include significant figures. Wave interference is a phenomenon that occurs when two waves collide with one another. Prior to the interference, both waves are just the way they were, regular waves going towards one another. However, when the waves are colliding, they create a resultant wave, which is the sum of their amplitudes. This interference could be considered constructive interference if both of the component waves' amplitudes are positive, or if they're both negative, because the resultant wave is larger than the individual component wave. However, it's considered destructive interference if one wave is positive and one wave is negative, because then the resultant wave is smaller than the component waves. An example of this is illustrated here. Waves A and B are going towards one another, and when they collide with one another, waves A and B, it's the sum of wave A and B. So this is an example of constructive interference. And after the interference, the waves continue moving on in the same directions that they were earlier. An example of this in the cruise ship is when you hear two sound waves interfere. When the people are on the bungee jump, it's natural for them to jump off, and when they jump off, it's natural for them to scream. So that's an example of a sound wave. But the diving board also makes a sound when it hits the mechanical stop. So when both of these sounds are coming at the same time, these sounds have constructive interference, and the resultant wave, what you hear, is louder than these individual component waves. Diffraction is a phenomenon that occurs when waves pass by a boundary. In diffraction, waves bend to fill in open spaces instead of having open gaps. So it appears that waves change direction. So when a wave goes by an open space, such as a doorway, the waves bend outward to fill in that open gap. And similarly, when it passes by a gap, it goes and fills in the spaces. So the waves are bending to fill in the spaces. An example of this is on the cruise ship, where the ping pong players are on the Machuca deck, which is below the ground and inside a room, or which is below the surface of the deck and inside a room. But they can still hear the bungee jumpers making the sound outside. So when the bungee jumpers are screaming, their sound is a wave, and the sound waves diffract throughout the ship. So they go through the doors and through the corridors and below the surface of the deck, through the openings, so that even if you're playing ping pong in another room, you can still hear the sound from outside. Simple harmonic motion is repetitive motion about a fixed point or zero reference level. This motion requires a restoring force that is proportional to the displacement away from the equilibrium position. And the restoring force must be also in the opposite direction as the particle's motion in order to ensure that the particle is oscillating back and forth around the equilibrium position. When playing ping pong, it's pretty common for the ball to hit the net. When the ball hits the net, it causes a disturbance that pushes the net outward. Using the elasticity of the net responds and goes back and forth. This is an example of simple harmonic motion because the position the net is usually in is the equilibrium position, and after the disturbance, which is the ball hitting the net, the restoring force, which is the elasticity of the net, brings the net back and forth so that the net moves in the motion that is simple harmonic, which is on both sides of the equilibrium position. Snell's law is a formula that is used to describe the relationship between the angles of incidence and the angles of refraction due to two given material properties of an object. And this is due to the reason for Snell's law is because the angles of refraction could be different because light rays in particular speed up or slow down in different materials. So if a wave speeds up, the angle of incidence will be larger, and if a wave slows down, then the angle of incidence will be smaller. Here's a diagram that illustrates Snell's law. So we see that the light ray is coming through, and then once it hits the material, which is likely water in this case, it bends toward the normal line, which means that the wave is slowing down. What this means is that N1, the index of refraction of the outer material, is smaller than the index of refraction of the blue material, which is N2. Snell's law states that N1 sine theta 1 equals N2 sine theta 2. We know that N1, the situation here is that the rider is coming down the water slide, and as they're coming down the water slide, they see something through the glass walls of the water slide at a 40-degree angle, and they want to know they know that the object is actually at a 40-degree angle, but they want to know what is the exact angle that they're seeing it at. So we know that N1, which is the index of refraction of air, is 0.000293, and N2, the index of refraction of crown glass, is 1.52. And theta 1, which is the actual angle, is 40 degrees. So when we plug this into the equation, we can use inverse sine to solve for theta 2. And we know that theta 2, which is the actual angle, or the angle at which the rider sees the object, is 25.028 degrees, or 25 degrees if we include significant figures. Thank you for watching.